Okay, moving on to our second keynote presentation for this session, Dr. Zia Emin from CIGRE. If you'd like to join me on the stage while I do the introduction. Dr. Zia Emin is the Technical Director on Power System Planning and Analysis with Power Systems Consultants UK since September 2016. From 2011 to 2016, he worked for Parsons Brickenhoff as Chief Power System Engineer, responsible for providing technical leadership in specialised power system study activities, where he led a diverse portfolio of projects in different geographic areas around the world. From 1997 to 2011, he was with National Grid UK, where he worked on many aspects of switching transients and more extensively on power quality issues. He undertook detailed analysis of the power quality of supply aspects of system performance for new connections, infrastructure and asset replacement schedules to ensure grid code compliance, while at the same time leading and setting policy in various power quality areas. He is a Fellow of the Institute of Engineering and Technology, IET, a Senior Member of IEEE, a Distinguished Member of CIGRE, and a Chartered Engineer in the United Kingdom. He is a member of GEL 210-12 Committee at the British Standards Institution. Task Force Leader and Convener within System Technical Performance Areas. He was the past UK representative on CIGRE SC C4 System Technical Performance and is currently the Chairman for the same study committee. He received the CIGRE Technical Committee Award in 2013, the Distinguished Members Award in 2014, and the Senior and Principal Professional Associates title within Parsons Brickenhoff, reflecting recognition of his technical and professional level. He has over 40 technical publications and is a reviewer of many technical journals of IET, IEEE, and other publishers. We welcome you to the stage and look forward to your presentation.
Thank you. I think the first thing I learned is I should cut my biography a little bit down. It's too long. Hello, everybody. I don't speak any of that Maori, so I'm afraid I can't say that. I do speak one or two other foreign languages, but I won't do it. I should start really by expressing my thanks to the organizers of this event for giving me and CIGRE the opportunity to explain the thinking and the work that's being carried out in relation to electrical systems of the future. Now, I landed to Wellington yesterday late afternoon, so I'm still jet lagged, and my body thinks that it's about 1 a.m., so if I start yawning, please don't laugh. Yeah. I'll start the talk with a relatively short information about CIGRE before really moving on to the challenges and key areas of transformation driven by these challenges. CIGRE, short for the French version of International Council on Large Electric Systems, was founded in 1921 in Paris as a not-for-profit professional organization established to promote the development of knowledge and exchange of information between engineering personnel, technical specialists, academics, policymakers, and regulators, and to deliver an unbiased summary of information from which opinions may be formed. Its current mission is to be the organization for technical reference for all aspects of electric power systems. With its vision to be universally recognized as the leading global organization for all electric power aspects, CIGRE aims to facilitate and develop the exchange of engineering knowledge and information on power systems, add value to knowledge and information exchanges by synthesizing state-of-the-art and world practices, to develop guidelines and information to aid the development of new technologies and to assist practitioners in their application. And lastly, to make its work available to the players of the electric power industry, specialists, as well as managers, decision makers, regulators, and academia. CIGRE achieves its technical work under the auspices of 16 study committees. And they are organized around the equipment, technologies, systems, and new materials and IT. These are the teams, the so-called A, B, C, and D teams, the committees. Approximately 230 working groups are constantly operating under the management of these study committees. And they are grouping around about 3,800 experts within the electrical energy sector from all over the world. And these experts are ideally positioned to express the views of industry and academia, of course. Now, the most recent figures count CIGRE membership at more than 14 equivalent members, composed of researchers, academics, engineers, technicians, suppliers, regulators, and other decision makers in over 90 countries. Now, having glimpsed into the CIGRE world a little bit, I think I will move on to the electricity supply or supplies of the future. Now, access to electricity in the developed world is a given. The system that supplies this energy has to do so in a reliable and most economic way with due care for the environment. These, of course, are conflicting requirements. But nevertheless, we all want access to that electricity, and that comes with challenges and changes. And the changes associated with these many developments bring challenges. Challenges associated with renewable energy sources, integration of renewable energy sources, and distributed generation into the grids, the intermittency of renewable power generation, policies for lower carbon and efficient energy use, challenges with transmission of large amounts of power over long distances, building new transmission infrastructures, keeping the existing power systems, and looking at the end-of-life grid renewal due to aging assets, challenges with increased customer participation and new needs for distribution grids, architecture of networks, methods to connect remote areas with no electricity, market design and regulatory mechanisms for an equitable, cost-effective transformation. Challenges due to progress in technology, including ICT and cybersecurity, and last but not least, challenges with environmental compliance and sustainability and growing environmental requirements. Clearly, of course, a transformation is taking place, and we at CIGRE believe that we are at the heart of this transformation. Now, these factors that we've been through, the challenges, suggest two network models for development with respect to the grids of the future. The increasing importance of large networks for bulk transmission capable of interconnecting load regions and large centralized renewable generation resources, including offshore, to provide more interconnections between countries and energy markets. The emergence of clusters of small, largely self-contained distribution networks, which include decentralized local generation, energy storage, and active customer participation, intelligently managed to be operated as active networks, providing local active and reactive support. Now, the most likely shape of the energy supply system of the future will include a mixture of the two, above two models. Since I think additional bulk interconnections and active distribution networks are needed in order to reach the ambitious environmental, economic, and security reliability targets that we are seeking. Now, the evolution of today's power system towards the two models, which we just described in the previous slide, is based on the 10 shown technical issues and the associated technical challenges with these issues. We'll now go through these 10 subject lines in turn to provide a very high-level CIGRE view on the know-how needed to manage the transition towards the electricity supply systems of the future. Now, bear in mind, different systems in the world may need to put more emphasis on some points and less on others. But we see relevance to all parts of the world from these technical issues. Starting with active distribution networks resulting in bidirectional power and data flows within distribution levels and to higher voltage networks. The key challenges at the very first word there, which appears the smartness, which I think everybody loves. The distribution systems will need more intelligence, of course, or smartness. The massive penetration of smaller units, generation, and intelligent loads imposes the need for their control and coordination. The coordination of a large number of small resources imposes a technical challenge that requires application of decentralized, intelligent control techniques in interaction with wholesale markets and transmission system management. The massive implementation of smart metering and demand-side response, metering that is used as information collectors for distribution network automation, home energy management, and electric vehicles. Potential evolution of market and regulatory arrangements to manage efficiency, equity, and cost recovery associated with active distribution networks. Distribution network architectures that support local energy balancing, including microgrids. New market-oriented control of distributed generators, such as virtual power plants, interacting with distribution grid operation as well as transmission grid operation. Solutions for remote microgrid connections, connections of remote areas with no access to electricity. The future works from CIGRE looks at modeling, analysis, and control, both centralized and decentralized, of active networks, and the interaction of information exchange between transmission and distribution system operators. The second area is the application of advanced metering and monitoring and the resulting massive need for exchange of information. New measured parameters, architectures of information, communication technologies, and algorithms for system operation, protection, maintenance, life management. Large amount of data exchange between an increasing number of stakeholders from distribution networks, dispersed generation, and consumption. Identification of the data to be exchanged and its requirements, such as volume, frequency, availability, security, confidentiality, etc. Disaster recovery and restoration plans, cybersecurity, and access control. It is noted that as modern power systems rely more and more on ICT technologies, the issues around communications, cybersecurity, are becoming increasingly important, and they will become a focus area in their own right in the future development of this work. The future work within CIGRE is concentrating on the Internet of Things and big data applications, effects on power system operation and control on transmission and distribution level. The third area challenge is the growth in the application of DC and power electronics at all voltage levels and its impact on power quality, system control, system security, and system standardization. Now, the expected increased use of DC at end-use premises, i.e. in home and commercial buildings, HVDC grids, LVDC grids, and the penetration of power electronics at medium and low voltage levels. The harmonic pollution caused by increased use of consumer electronics. DC and PE-based generation has, of course, significantly different dynamic response and performance than conventional generation and AC lines during faults in the AC network. In many cases, of course, if applied with judicious and properly coordinated design and controls, these technologies can provide great benefits and performance enhancement to overall system reliability. HVDC grids are a new and different application of HVDC and require standards and grid codes to enable the grid to be built gradually and with the flexibility of utilizing equipment from different manufacturers, similar to the AC applications. The future work in this area is at the moment concentrates on the study of AC network performance with appropriate control models of high voltage DC and power electronic systems. The fourth area is the need for the development and significant installation of energy storage systems and the impact this can have on the power system development and operation. The key challenges concentrate on the construction and operational issues. On the construction side, it's the advanced materials for construction, the reduction of installation and construction costs, reduction of environmental impact, and increased use of recycling, improvement of efficiency of charge-discharge cycles, reduction of energy losses, a decrease in weight and increase of size density, aging mechanisms, development of lifetime estimation models. At operational level, modeling for steady state and dynamic simulations, management of storage for peak shaving, ancillary services, renewable energy source balancing and energy arbitrage, cooperation with demand-side management, development of pump storage and battery storage applications in autonomous power systems such as island systems, and management of charge-discharge cycle, sizing, and siting of storage devices, impact this will have within all voltage levels, and cooperation with renewable energy sources for hybrid systems, use of photovoltaic systems, for example, to charge storage during the day or when available for later use. The future work at the moment concentrates on the development in storage technologies regarding materials and methods and storage analytical models and the storage solutions connected via power electronics for reactive power management, i.e. the ability to reduce peaks. Storage integration at transmission, distribution, and demand side, and new market products to enhance flexibility, i.e. frequency control. The fifth area is the new concepts for system operation and control and market regulatory design to take account of active customer interactions and different generation types. Operational challenges by combination of stochastic generation and modified loads due to flexible loads and energy storage, the power balancing, the congestion management, evolution of market design and regulatory mechanisms to promote market participation of renewable energy sources and consumer involvement, active and reactive power reserves, risk management in probabilistic approaches. Moving on to evolution of power system control, the integration of power electronics-based technology in transmission system, including HVDC links inside meshed interconnected systems, which creates challenges regarding reliability, market integration and control, and impacts the dynamic behavior of the power system. Awareness of overall system status can be improved at. Do we extend it to the continental, national, regional, and local level? The need of common and coordination activities among transmission system operators and distribution system operators, market operators, energy service providers, and other stakeholders. Need to define boundaries between systems on information, exchange, and operational interfaces between TSO, DSO, and other factors. In other words, production and load centers. Increased level of automation in control room. New software tools, for example, to quickly determine the status of the system over wide areas, providing decision support and increasing the awareness of system operators. Automated configuration and electrical parameter adjustment, automated service restoration, and adapted disaster recovery scenarios. You can think of about inertia, synthetic inertia, and rock-off, which we are all aware of, the buzzwords. And lastly, the ensuring competencies of control room-based system operators and adopt their training for their needs. The current work within CIGRE at the moment concentrates mainly on critical infrastructure protection against cyber attacks, and we all know what happened 2-3 weeks ago in UK and worldwide in terms of cyber attacks, so no need to mention further. Ancillary services from power electronics interfaced intermittent generation, flexible consumption and storage, and harmonization of grid codes for renewable energy sources connecting to the grid. And lastly, the adaptive protection systems according to network operational conditions. Moving on to the sixth item, which is the new concepts for protection to respond to the developing grid and different characteristics of generation. New wide area protection systems for transmission to overcome limitations of special protection schemes in terms of reliability, flexibility, and maintenance costs. Impact of power electronic-based generation on the protection system due to decreasing short-circuit power and flow reversal. Capabilities for fault right-through, i.e. capabilities of new generators to withstand low voltages due to faults without disconnecting, the coordination between protection and new generation capabilities. The inadvertent islanding detection and intentional islanded operation, i.e. situations when part of the distribution network operates without connection with the higher voltage network as a physical island. New protection and automation functions for distribution networks using powerful communication networks. The existing work at the moment concentrates on new wide area protection systems, protection of new generation technologies and their coordination with system protection, integration of protection and automation with innovative power electronic technologies, for example, rapid under-frequency operation, and adaptive protection and automation functions for distribution networks, metering as information collectors for distribution networks automation, home energy management, and electric vehicles, data management and architecture of the future. Innovative technologies such as DC circuit breakers all fall under the new concepts for protection. The seventh item in terms of challenge is the new concepts in planning to take into account the new transmission distribution interfaces, increasing environmental constraints, and the new technology solutions for active and reactive power flow control. Now, planning and approvals under increasing uncertainty, the changing role of the power system and changing nature of supply and demand impact the ability to plan to minimize asset stranding while maintaining reliability and quality. Uncertainties, of course, are very high and affect so many economic and technical factors that taking them into account in the planning environment is a major need and challenge. Higher community awareness for environmental factors. This drives many of the developments. For example, for transmission lines, transmission line approvals, technology or equipment choices, and design such as switchgear insulating gas. Changes in technology, the need to understand costs, capabilities, and lead times of each solution to enable comparison between options. And changing economic drivers, which impacts availability of funding and investment risks and can have major impacts on investments, especially in market-based systems. And changing market and regulatory environment, impacts on level of central planning versus market solutions. We keep learning about the advantages and disadvantages and combinations of central planning versus market solutions under changing market and regulatory environments. The nature of supply and demand, including demand response, transport electrification, all increases uncertainty of long-term solutions, potential, of course, for asset stranding. The future work at the moment in the planning area is sort of concentrating on the interaction in network investment planning, given demand response, possible electrification of heating, cooling and transport, and distributed generation, and given the much higher aggregate length of distribution lines compared to transmission lines, the interaction of transmission and distribution expansion investments needs to be addressed. Best use of existing assets by extending asset useful life and by adopting assets to new requirements, i.e. bidirectional power flow, by asset updating or upgrading, new control systems, for example, and if possible, by their redeployment. Reliability assessments, end-of-life management of aging assets, including transmission and distribution equipment, and big data analysis for asset management. The list can be extended to include single-phase analysis, integration of microgrids in planning, load and voltage determination, or the integration of HVDC grids and AC networks within the planning concept. The eighth challenge area is the new tools for system technical performance assessment because of new customer, generation, and network characteristics. The key challenges are the advanced numerical techniques and numerical methods for the solution of dynamic problems in integrated timeframes and multi-phase power flow problems, advanced tools and techniques for power balancing and reserve requirement evaluation, advanced load modeling techniques, techniques to model decentralized control applications, i.e. functions with a limited perception of the environment able to take intelligent decisions, such as multi-agent techniques, planning and operational tools which can optimize the overall performance of the network and help to manage uncertainty based on monitoring data and the application of failure mode and effect analysis to characterize the actual network performance of new and existing technologies. In other words, a probabilistic and risk-based planning. Modeling of active and adaptive control strategies, centralized control systems, grid-friendly appliances, and demand-side management. Models for new and advanced technologies. Co-simulation platforms that can integrate the simulation of both transmission systems and distribution systems. The existing work at the moment concentrates on bridging the gap between the electromagnetic, EMT, and three-phase, and then positive sequence modeling and simulation tools. Hardware in the loop simulation tools that can interface physical hardware equipment with real-time digital simulators, the RTDS, in order to potentially reduce performance demonstration times. Tools and techniques for assessing the harmonic performance, for example, of the grid in light of the greater DC and power electronic penetration at all voltage levels, plus geographical information system-based tools. Models for assessing the interaction between the AC system and the HVDC converter stations, HVDC grids, and fax devices. They're all being looked at the moment as we speak under this technical performance challenge. The ninth challenge is the increased use of right-of-way capacity and use of overhead, underground, and subsea infrastructure, and its consequence on the technical performance and reliability of the network. Now, technologies for operating existing overhead lines, they're replacing the old conductors by high-temperature conductors and retensioning of existing conductors at overhead lines, upgrading voltage level, using real-time thermal monitoring, probabilistic ratings, conversion of AC to DC lines, considering hybrid lines, both AC and DC on the same tower, compact lines, and aesthetic supports for the overhead lines, development of new insulated AC or DC submarine and underground cables for high voltage applications, such as offshore wind farms, consideration of on-sea infrastructure with offshore developments in wind farm solution for substations and cables, including both transmission and distribution, use of wind load data for design criteria, for example, for submarine cables, compact design of converter stations for offshore and urban applications, increased use of interconnections and their implications on planning, operation and control, and the establishment of electricity markets, use of overload capacity and thermal transient calculations of underground systems, which impact on the design criteria of underground sections, Design criteria installation technologies for deep water cables to enable relevant interconnections, inclusive of requirements for T&D equipment in changing network conditions. Investigating the ability for all components to withstand transients and overvoltages. And of course, incorporation of intelligence into T&D equipment. Sorry, I've been going a bit faster. So moving on to the 10th area, which is an increasing need for keeping stakeholders aware of the technical and commercial consequences and keeping them engaged during the development of the network of the future. Now, environmental aspects such as nature, fauna, flora, EMF, audible noise, visual impact, etc., are of course among the main drivers in terms of stakeholder awareness, but also main objections against energy projects worldwide in terms of production and transmission, and it's becoming increasingly important. Environmental considerations are a main driver for the development of the sustainable energy systems of the future. This is now obviously increasingly understood by the electricity sector, which you all represent, but also driven by the outside world, i.e. the politicians, the NGOs, and other stakeholders like the financial world who are investing for, say, offshore wind farms. The key challenges in terms of the measures that need to be taken by the industry in the planning phase is to demonstrate the usefulness and the benefits which will result from the project, and to guarantee that sustainable development principles and issues are being incorporated at planning stage. To take into account public views, consultation and needs already in the system at planning and design and options. And in the construction and operational phases, to demonstrate the compliance with environmental standards. And to obtain support for the necessary actions, for example, for maintenance. In terms of future work that's being undertaken, the most important undertaking will be really engagement, to sum it in one word. A development of electricity systems of the future requires extensive engagement with key stakeholders to ensure the required investments receive government and community support and gain access to scarce capital. I've now come to the last slide, and glad to see that everybody is still awake. So these 20 technical issues, 10, yeah? They already intersect the 16 CIGRE study committees, demonstrating how the CIGRE work really supports development of the electricity supply systems of the future. Now, through the products CIGRE is creating and will continue to create in future years, the governments, regulating authorities, system planners and operators, equipment designers, vendors, academics and consultants, and other stakeholders like investors, general public, NGOs, will be equipped with valuable published resources on these very diverse technical aspects of the future system. We hope and anticipate it will guide their decisions towards optimal reliability, security, economy, sustainability, and environmental and customer friendliness of the future systems. That concludes my keynote, but I have one more slide which I've been asked by the New Zealand Committee of CIGRE to show, and that is to say there is an event, a CIGRE event here in New Zealand, Auckland, in September, which brings together a colloquium of Study Committee B5, which is for protection, automation and control, and a meeting of the CIGRE Administrative Council here in New Zealand, and also a technical meeting for a regional CIGRE committee, the Asia-Oceania Regional Council, which is all taking place at the same time, 11 to 15 September 2017. With that, I conclude. Thank you.
Thank you very much, Zia. Now we have time for some questions.
Yes, please.
Over to the floor.
Thank you for that. Very interesting, and you covered off a lot of points that we are observing. Sorry, my name is Tim George from Digsland Pacific in Australia, where we don't know how to sail, apparently. But my real point that I'd like to make is that you've covered off a lot of issues which are highly relevant. The issue is timescale. What we're finding in Australia at the moment is that people are investing in solar, in particular, at a rate which is, really quite frightening. There's thousands and thousands of megawatts of PV that's going in. So we're seeing, when we're doing the connection studies, that at the same site we may be having problems with high fault levels at night and very low fault levels during the day, where we're getting short circuit ratios which might be dropping down to less than 2. And the consequent, yes, I know CIGRE have got a very nice document out about wind farms connecting in low short circuit ratios, and we reference that, and it's very interesting, and their concern is for fault levels of about 3, short circuit ratios of about 3. But here's a situation where things are happening so fast that these timelines that are perceived in your presentation are just no longer applicable. Stuff has to be decided and research has to be done in a very tight time frame.
Correct.
To work out how to operate the power system under these very new conditions. I'm just interested in your observations, particularly on the timeline of how you solve these problems.
Well, this is beyond this presentation really, but there is an initiative within CIGRE to try and reduce the timeline of working groups to try and produce something useful much, much quickly. And at the moment, the tendency is to try and push it to 2 years from the start to the end product. Whether that will happen or not, I don't know, because one of the things that we have to remember is that the work that is being carried out is all on a voluntary basis. So it's very difficult to motivate people, and different parts of the world have different agenda, of course. But I 100% agree with the observation that sometimes it's coming a bit too late.
Once again, I'm bemused. In my 60 years in the industry, all new technologies have come on because they were better, cheaper, and more reliable. As you say, the objective is a reliable and economic supply. You're talking about imposing on the industry 2 unreliable and uneconomic sources like wind and solar, which only exist because they're subsidized. And then you're talking about spending even more money trying to adapt the power system to take something that's totally uneconomic anyway. When are the institutions like yours and the IEE and the IEEE going to get up on their hind legs and say to the governments, you are heading on a downhill spiral of increasing electricity costs and decreasing reliability, and if you continue, there's going to be a consumer revolt and the whole thing's going to collapse? When is someone going to wake up to the realities of the situation?
I can answer the question in 2 ways. At personal level, I agree with what you said. But I think it's not CIGRE really which is sort of trying to sell this idea. It's happening. It's happening everywhere continuously. But there's one thing I think we are missing, which is when you look at the overall world, the whole world, and the penetration of power electronic-based generation, the wind and solar, it's in single digits really. So much of the world is still relying on the conventional energy. What we are trying to do here is to try and come up with a collective knowledge sharing in what's happening in certain parts of the world, obviously Europe being one of them. You're free to take it as it is, or you can just ignore it, but it is happening. And therefore, there needs to be some form of knowledge exchange between various parts of the world and experts, so as we can understand this much more quickly, as opposed to like waiting 3-4 years. We better act now.
We're all giving the appearance of actively going along with this nonsense. Yes, we do have to go along with it, but we can say it is nonsense. This is what we're supposed to be. We're the technological leaders of the world. We're supposed to tell the world the implications of what they're doing.
Yeah. As CIGRE, we cannot have a position paper on these things. CIGRE decided not to have any position paper. So we are just there to disseminate information. IET and IEEE might approach differently because they are there to advise governments on policy issues as well. But to Phil, I think you had a question about subsidy being withdrawn and things are not sort of moving forward. I think in the last month or so, one of the wind farm developers in Europe, they went subsidy-free in Germany with one of the wind farms. Dong Energy, as far as I can remember. They are going without any subsidy to install and start operating one of the wind farms. We have to wait and see what will happen.
In Spain, since 2013, wind and solar development have stopped. They withdrew the subsidies. That's enough.
Okay, well, look, we need to bring this to a close. Is there one more question? Okay, yeah, so we'll just take this last question. Thank you.
Hey, this is Janos from Meridian Energy. I've been coming to this conference for a few years now, and just on behalf of every young engineer in the room, I'd like to apologise for our eccentric old grandfather over there, who'll be dead before long before all of us, and we'll have to deal with all the problems and all the really interesting challenges that you presented. So really appreciate the work you guys are doing and the rest of the CIGRE group, and yeah, thanks very much.
Thank you.
I'm not sure that was a question, but we'll take it for what it was. Look, could I ask Richard Pearce to come to the stage to propose a vote of thanks?
Thanks, Bob. Thank you very much, Zia. It's my pleasure to propose a vote of thanks on behalf of the Electricity Engineers Association today for a very informative and keynote address. And you've shared many valuable insights into the work CIGRE is undertaking on the challenge of transitioning to electricity supply systems of the future. In particular, you've highlighted 10 areas of focus, and for such a transition, you've stepped us through the challenges associated with each of those. The subject matter extends across supply side, demand side, markets, regulatory, technology, environmental, sustainability, and it addresses many complex areas for our consideration going forward. So thank you for sharing those insights with us. Thank you also for travelling to New Zealand and for joining us at the conference this week, and we very much appreciate your input and your insights, and I hope the jet lag subsides well in time for you to get on a plane and return home. One more comment, very good. Please join me in thanking Zia for his keynote presentation.